Dobra, to do tego mówię. Halo? Też dobrze. Jeszcze to zapytam. To co, można już? Dobra, to jedziemy. Ladies and gentlemen, I hope you enjoyed your lunch. Now I got two announcements before we kick off with the next session. The first announcement is about the money, as usual. Here at the Military Institute of Aviation Medicine, we are planning to protect our past. This is also something about our sessions from past, present to the future. We had a very glorious past, the old centrifuge, in which General Hermaszewski was trained and some other cosmonauts from the other times. We want to refurbish it. We want to make it a kind of memory place. And here you got, okay, in very small letters, but it will be published later. We are gathering money for this purpose. So if you could donate or find the donors, find a way to help us with saving our flight heritage, we will truly, truly appreciate it. Thank you very much in advance. And the next slide, please. Nie to, pardon. Ten, co teraz jest na laptopie?
Ten, co jest na tym.
O czasopiśmie?
Czasopismo.
And yet another announcement. We kindly invite you to publish in our Polish Journal of Aviation Medicine, Bioengineering and Psychology. And Colonel Rafał Lewkowicz, please stand up. He's the editor-chief. So should you be interested in publication in this glorious magazine, it has 70 points of 70 ministerial points, so it's national points. So it's ranked pretty high nationally. So please refer to Colonel Lewkowicz. Thank you very much. I tried to make it as short as possible. And now we are moving towards our next session. Thank you.
All right. Welcome again. Hope everyone has a nice, has this nice warm fuzzy feeling in their belly. But I hope you had coffee and you're ready to hear some more. It's okay. We're going to sort it. So we're going to carry on with the session about the Polish experiments on the International Space Station during the Ignis mission. And there's going to be a slight change in the sequence of presentations. We're going to start with thoughts over gravity, a test of using fNIRS, I hope I'm pronouncing it right, base brain-computer interface in LEO conditions. But hopefully Dariusz Zapała is going to make it easier than me when I try to pronounce the title of the presentation.
Okay, thank you very much for the invitation. I'm really happy to present today the results from our experiments about using the fNIRS technology, functional near-infrared spectroscopy, in some specific goal. I mean, we use this technology to control some application only by the modulation of the brain activity. And I represent the Cortivision, the company, the manufacturer of fNIRS devices. So all of these devices and the software is developed by our company. Okay, so first of all, really basic about the idea of fNIRS measurement. So all of us know that the body tissue is partially transparent for the light, visible light. We can easily see. But in the same time, if we use the near-infrared light, it's much more informative in terms of how we can use this light spectrum to measure brain activity. Why? Because oxy and deoxyhemoglobin can absorb different wavelengths of near-infrared spectrum. So if we put the emitter of infrared light on the scalp, send the infrared light through the brain tissue, then we can measure also on the surface the difference between the emission and the light intensity using the detector on the surface. So because we know this, and we have some assumption about the absorption by oxy and deoxyhemoglobin, we can estimate a relative change in hemoglobin concentration. And why it's quite interesting technology, just because we measure this kind of the signal, the metabolic change, that highly correlate with the results from fMRI. And we know that there is a lot of knowledge about the brain activity that came from the fMRI world. And now we can measure similar change, the bold signaled changes, using the technology that can be mobile. I mean, we can measure this brain activity. Of course, only the superficial layer or the cortex. It's not possible to measure the deep structure in the brain, but a lot of interesting things are in the cortex too. So we can use the fNIRS to measure exactly the same, using exactly the same procedure, and reproduce some effects that we observe in fMRI. And of course, the fMRI is really difficult to send to ISS. So this kind of technology, of course, not with, as you can see, the spatial resolution is not so high like for the MRI, but still we are better in terms of the localization of the source of the brain activity than EEG, for example. Of course, the EEGs, we measure the bioelectrical activity. Here we measure the metabolic change, but the attractive part is that we measure the similar things like fMRI. Okay, so our company was the first company that sent the fNIRS on ISS during the Axiom 2 mission. Together with Saudi Arabian research team. And after this experience with Axiom 2, Axiom Space asked us to support the next Axiom mission, Axiom 3. So there was also the chance to support the Swedish team in the registration of the brain activity in the next year, in 2024. So this is our heritage in supporting the brain monitoring in the space condition. And you can see here the difference between the two experiments in terms of the environment, because in the first experiment, we start with placing the emitters and detectors. You can see that we use the similar caps like EEG. But the sensors, emitters and detectors are different, of course. But the things like, it's very attractive in measurement the brain activity in a space that is quite resistant for the movement artifacts. And the other thing is that we don't need any gel, and the gel is quite problematic in a space station. So in the first experiment, the two astronauts, they support each other in terms of the placing the emitters and detectors, but the result was quite good in terms of the performance as a signal quality. So for the next experiment, we try also check if it's possible to wear and secure the sensor only by the astronaut on themselves. So even without any support, in a relatively short time, it was possible to make sure that signal quality is sufficient for the analysis. So I also maybe mention about the goal of the two experiments. Of the first experiment was as a first use of fNIRS technology in a space condition. We compare the difference between the Earth and the space condition in some cognitive tasks. And in the second experiment, there was a comparison between the different space modules, and by space modules I mean the different environmental conditions of the station, also during the cognitive task. And this is ongoing experiment, so they still collected data, and our device is on ISS as a permanent device. But during the IGNIS mission, we tried to move from the provider of technology to full author of the experiment. So we apply with our experiment the photon graph because we want to make a first brain-computer interface communication tested in space condition. What is the brain-computer interfaces? So brain-computer interfaces is this kind of systems that allows us to control some application or some devices only by the modulation of brain activity. And we can measure this brain activity using EEG, fNIRS, fMRI. The different kind of modalities can be used to measure the brain activity modulation. And then we need to find some features that we can use to control something. So we need at least 0 and 1 to control anything, the device or the application. So we need to find the features in the signal that represent this 0 and 1. And then we need to use the machine learning algorithms to recognize in continuous monitoring what kind of the brain activity belongs to first or the second category. Because if we know and the classification is successful, we can control some objects, some application, only without any muscle activity, actually. In our experiment, we use two different tasks to evoke these brain states to modulate brain activity and then control the objects in the application. And we're monitoring the two brain areas. Dorsolateral prefrontal cortex. This brain area is more active in more demanding tasks. So we try to evoke the cognitive load by the task of the multiplication of two-digit numbers. So the participant needs to mentally solve this task, of course in the sequence, and then we try, during the calibration, we try to find the brain activity patterns that represent the cognitive load. And in the second condition, it was simply relaxed, because during the relax we observed the decrease of the activity dorsolateral prefrontal cortex, but in the same time there is an increase of activity of medial prefrontal cortex, the green one. So we have our 0 and 1. So now we can control some object, some application, and the application looks like this. So there was a two icons. One represent the, let's say, meditation, so it's for the relax, and the second one was this dart. which target represent the focus, so the cognitive load. So we present one or the another one icon on the screen, and astronauts need to focus or relax, and our algorithm try to recognize the brain pattern, and then we use this brain activity to control something. And in the same time, we also measure the accuracy in the task. I mean, if they really mentally solve the problem, I mean the multiplication during the test. So there was two measurements, the brain activity and the accuracy of the response in a task. And first thing, what is always important for the brain activity monitoring is, of course, the signal quality. So we compare the signal quality, one of the measurement of the indicator of the signal quality for the fNIRS is called the coupling index, and this is the correlation between the oxy and deoxyhemoglobin wavelengths active for the both chromas. And there was no difference between the session on Earth and on ISS, so it was quite similar to results from our previous experiments on IX2 and IX3. So the signal quality was sufficient for to evaluate the rest of the hypothesis. So the most important thing in terms of this experiment was to see the effectiveness of this kind of communication, because as you can, as you know, of course, if we need to control something, but there is a lot of errors. I mean, the mismatch between our goals, I mean, what we want to achieve by brain activation modulation, and the response of the algorithm, I mean, how algorithm classify the signal, is not useful for the communication. So we need to increase the what we call the BCI performance, or brain-computer interface performance, so the accuracy of this recognition, the brain states, the classification of the brain states. And in this particular experiment, the level of chance, so the something that is the threshold for us, as to say that, okay, our BCI is effective, is 0.7 of accuracy, and the session from photon graph experiment as above this threshold and is a significant result. And in the same time, we'll also compare the results from Earth and from the space conditions. And there was no significant difference between the space and Earth in terms of the effectiveness of the brain-computer interface communication. Of course, we find some difference in terms, but not significant in terms of the hemodynamic response. But of course, as was mentioned at the beginning of today's sessions, there is obvious difference in terms of the how the blood behave in the microgravity. So probably this kind of difference is driven by blood volume changes. Okay, what's more? So here is the correlation between the BCI performance, so the classification from the machine learning algorithm, and on the second axis, there is the response accuracy. So you can see that there is a quite nice correlation between how participants respond in the task, so they are effective or not in terms of the mental task, and BCI performance. So let's say we can say that we can predict even the accuracy of response in the mental task based only by brain activity. So this was the second goal of the experiment. And we also find some quite significant difference in terms of the performance between the participant in the BCI performance and the response accuracy. And I would say that if we compare the bold signal changes between the two participants, we can easily see that the activation, the patterns that we find we find as a final results is driven by simply the ability to concentrate on the task, let's say. Okay, the last thing is how they perceive the mental efforts or task load during the BCA communication. If you want to control something in the space condition, of course, using the BCI, we need to solve this problem first, if they want to use this technology for communication or not. So here you see the workload from the questionnaire, and the green, the red line, dashed line, represent very, and maybe not very, but medium task load. So let's say the physical demanding or was not very high in this kind of task, but in the same time, mental demanding was above the blue line, which represented high task load. So in a conclusion, I would say that this is quite promising results in terms of the brain-computer interface communication in a space condition, but in the same time, we need to pay more attention on the task load, because you can imagine that mental multiplication is not something that is very easy to perform in the space conditions. Thank you. I just want to mention that it's not our end of our journey with the support brain monitoring in the space. We cooperate with Axiom Space permanently. So if you have any idea for the next experiment on ISS and you need some brain monitoring for that, just please contact us. Thank you so much.
Okay, just wanted to confirm that you'll have a chance to ask questions. So yes, Dariusz will stay with us until the end of the session. So we'll move on to the next presentation. It's going to be Marcin Dornowski with EEG Neurofeedback. The floor is yours.
Thank you, Caroline, for introducing. I'm from Gdańsk University of Physical Education and Sports, so I promise it will be quick and accurate. It is a complete privilege to be standing here in front of you and to be able to share my thoughts, experience, and just some of the results from the experiment that was executed during Ignis Axiom formation this year. On this slide, you are able to see the full title of the experiment, which is long. The short version, Neurofeedback EEG, please do not kill me, because each psychiatrist and each psychologist will tell me Neurofeedback EEG, really? It should be biofeedback EEG or just neurofeedback. But some of higher heads in NASA said it will be more media. So it stayed neurofeedback EEG. How it happened? 6 years ago, I would say my mentor, great psychologist from Poland, Professor Pąchalska from Krakow, she pointed her finger on me, her scientific finger and said, you will work with neurofeedback and you will work with science, with the space sector. I was just smiling and that it will be just like riding a goat during the winter for me. No way. But after 6 years, I'm standing here after the experiment, after a huge amount of work. As we can all know, it was all day and night work to do and to be here and to be able to share with you with our experience. So, am I happy? Yes, I am. Am I tired? Yes, I am. Would I do it again? Yes, I would. There are many solutions for dealing with stress that we know already. We can meditate, we can use physical activity protocols. I'm from University of Sport, University of Physical Education and Sport, so I know that. You can use pharmacological intervention. But is there any solution which is fast, not so priceful, it's rather cheap and effective? So I have just remembered the word from Professor Pochalska. Yes, it is neurofeedback. So first of all, thank you, Agata. We have started to cooperate with the habitat in Piła, Lunares. We've done several analog missions. We've done several missions in Switzerland, and we have done the same procedure in Piła and in Switzerland as we did in ISS. After 5 or 6 analog missions, we knew that neurofeedback EEG, let's say that, or biofeedback EEG, is working. Our goal and aim was not to check if it is working. It is working, but how it will be working during actual space missions and how it will work according to different kind of spheres of human body, human functions. That was the main idea. We've done several papers after the analog missions, which gave us kind of a lift off to and motivation to apply for POLSA and then ESA and then NASA to became one of 13 experiments on ISS, and it happened. Two main goals. We didn't want to prove that neurofeedback EEG works. It's working. We knew that from a literature overview with from our experiments, but is it working upstairs on ISS? That was the main question. The second question was, how does it work in different spheres of human activity, human parts of the body, Would it be the same or not? We decided to divide all the parts into 4 or 5 sections: psychological, biochemical, psychomotoric, neurophysiological, and to each we selected control methods which could give us an answer if it's working and on which level it will work. We've got the answer. So far, we are not able to give you all the information, but believe me, at the end of the year or just the beginning of the next year, it will be possible. Material of our experiment. The first, we all know. The second, we still have to say in Polish, pomidor or tomato. We do not have permission to say who was it. Was it a female? Was it a male? I can't say. So there were 2 astronauts. One of them executed real neurofeedback, and one of them executed double-blinded placebo neurofeedback. So I hope we will be able to know, is it really working upstairs or not? That's our team. Just 4 people, but I think that it is enough to be successful. But as we all know, all PIs knows that if you are a PI, you will work by yourself. I hope not in each experiment, but I had to do it. There are neurophysiologists, there are psychologists, clinical psychologists, there are person responsible for all the equipment and IT stuff. So I think, and I know, and I'm sure that all procedures from our experiment were done perfectly. The one and the main thing that we were concerned was, will each device work? If one of device wouldn't work in Houston, in Colonia, in Poland, the experiment is off. All devices had to be in perfect condition. They were new, but as you can know, everything can happen, and that was the main issue, drilling a hole in my head. I don't have a hole in my head right now, so it all happened perfectly okay. One of the most important slides, just let me. The experiment was divided into 3 phases: before mission, after the mission, and just slide before the mission. Before the mission, we executed several control methods which could give us or gave us information, specific baseline according to all the psychomotoric, psychological, biochemical, neurophysiological spheres. We knew how their bodies work. Then we prepared all 2 astronauts to execute neurofeedback during quarantine. And a lot of people on this audience knew that a visit in Florida was not a vacation, but was very stressful 2 weeks of waiting for a departure, because we had to know that all experiments will work. Each day could destroy experiment. But it happened. So we are just here and are able to speak about the experiments results. As you can see, we've done some CRP level evaluation. We've done some Vienna test system 2 tests for psychomotor evaluation. We have done EMG together with Vienna test system evaluation of muscle activity. We have done a lot of questionnaires. They love questionnaires. And the green, I suppose, the green, neurofeedback training. So during quarantine, they performed by themselves. They were taught how to do it. They performed a special number of training sessions before the departure. So that was the crucial moment of the experiment. The next one, well, during the mission, we wouldn't like to give them any specific tasks to do. They had to execute just one questionnaire. We would like to know the dynamics of the mood during all the mission. So that was the one method used on ISS. After the mission, we had to repeat all the measurements that were performed before the mission. So we had to go to Houston, we had to go to Cologne, we had to take all the equipments. Also have in mind, will it work? Will they pass us to the borders? It all happened wonderfully, great. We were happy. We came back from Houston and from Cologne with big smiles, because we had all the results from the all working devices. So after the mission, we have repeated that's your fault. We have repeated all the measurements. Few results. Please give me a time, give us a time to select all the factors, all the parameters that the amount of these parameters is just overwhelming. So we have to select the most significant. We have to do a specific analysis, statistical analysis, but here you can see that, for example, CRP reduction, 25% in the astronaut who was under neurofeedback intervention. Huge information. There are also improvements in scales of 2 questionnaires. We hope that we will also have good results out of EMG results connected with Vienna test system, and also with the rest of questionnaires. Together, we would like to create one significant sentence. It's working, and we would like to implement very easy method to overcome stress, in a negative stress influence on astronauts, or maybe another professions where stress is involved, just to be an effective as before the stressor appear. That's the main goal we would like to achieve from our papers and from our today's presentations. The last word. We would like to implement it into a widely understood sphere of national defense, because there are stressors that influence on efficiency of the execution of difficult tasks. Why, if we have a device, if we have procedure, if we have a personnel to do so, why don't we use it? So please use it with us. Thank you very much.
Thank you, Marcin. And for the last presentation, the MXene in Leo, a technology demonstration of nano-biomaterial device in the ISS with Axiom 4 mission, Shreyas Srivatsa.
Good afternoon. I thank the organizers for giving me an opportunity to present MXene in Leo to the audience here in Poland, and thank you for your patient listening, because it's going to be a 15-minute fast racing event that I'm going to take you through. So maybe just to introduce myself, I'm Shreyas Srivatsa. I work at AGH University of Krakow. So what are MXenes? You've been hearing about it for several times, and what are the wearable devices that we tested in the ISS? How is that useful for the space medicine community? What are we looking at as a future for using this technology in Poland and also elsewhere? So let me first take you through the last 7 years of what we've done. So we have, I started, I think, work in 2018 when I was here for the Mercury Fellowship, and we started working with MXenes. We prepare MXenes, use them as applications for the terrestrial applications. We have also done testing in stratosphere for the same material, and now we've tested it in the ISS. So what are MXenes? MXenes are basically a two-dimensional nanomaterial. So nanomaterials are materials which have at least one dimension in the nanometer scale. So in MXenes, they're two-dimensional, where you can have the thickness which is close to a few nanometers, while the length and the width, the lateral dimension, is basically a few microns or micrometers. So they are a combination of metal carbides, metal nitrides, and metal carbonitrides. So the M in MXene stands for metal, transition metal. X stands for carbide or nitrides. EN is just basically derived from graphene, and we've used it for MXenes. First reported in 2011 in University of Drexel, and then they're very eye-catching for several of its physical properties. They've been very popular for the last decade and more, because they have good hydrophilicity. So basically, they mix well with water. They also have flexible behavior, where you can take them to very high tensile stress. They're also highly conductive, which makes them very useful for several applications that we'll be talking about today. And this has led the community to work on several types of composites, as well as using this material for several applications. Our focus at AGH was to see how we can make sensors out of this, understand the behavior of the material. So to develop any sensing material, you need to know how does it operate in various environments. So if you're considering space, you have large temperature range, changes with pressure, off-gassing. All of these need to be studied for a material for it to be classified for spaceflight. So basically, MXenes have had several applications. they're used as 5G antennas. They're used for electromagnetic shielding of space equipments, military equipments. They're also used as implantable devices. So there is also several studies where implantable devices with MXenes are being tested clinically. There's also sensors which are developed for human wearable devices, also for pressure sensing, temperature sensing, humidity sensing. All of this has been done. There's also optoelectronic properties where they're used for IR camouflage applications. There's also work on environmental use where you can use them as filters to filter water and substrates that you want. The MXene-based films are also used as artificial kidneys. So they're used for removing urea from the blood in the process for dialysis. So there is a lot of applications that has been there in the last decade and more. And our focus at AGH has been mostly to build everything from scratch, have MXenes made in AGH in Poland where we can synthesize, process the material as we want, and then use that for applications. But this also needs to be in a context where it is repeatable, reproducible, and this has been the challenge for nanomaterials for the last 2 decades, where can you use nanomaterials in large-scale equipments? So imagine I want to paint nanomaterials on a wind turbine, on an aircraft. So can it be repeatable? Can it be giving us results which can be useful for applications? So this has been the challenge we tackled for the last 7 years. So we have quality control that we do after every sample is produced. So we can produce about 5 grams of this material for one cycle. So about 2 days is required to make 5 grams of this material. We characterize the material, qualify that, okay, this has certain parameters that can qualify it to be used for application, and then we build sensors out of it. We can also understand the physical properties of it. So basically, we have studied several types of physical properties. So we have had a long temperature range from about 10 Kelvin to about 300, 350 Kelvin. We have tried to understand how the electrical properties of fundamentally resistance of this material changes with such large temperature range. We've also found the thermal conductivity. So if you want to have this as thermal conductive material, is it good or bad? So we have some answers for that. We have also used that in low temperature for magnetic field. So if you apply a magnetic field on MXenes in low temperature, how does it behave? So these are some of the things that we repeated to understand if we can reproduce the results from the literature, but we've also been contributing to literature with the first reporting of the dynamic response. So if you want to build any sensor that works in a quick dynamic range of microseconds or milliseconds, so which means do you have to capture the force acting on maybe a collision between 2 cars. So if you have to measure that, the sensing should also happen in the same time frame. So that was the first understanding that we gained from this material. Then we have also reported the specific heat of this material, which is critical for its thermal property estimation, and also for several theoretical studies that can be done based on that. We also have the Seebeck effect, where we can understand how heating equipments can be made using MXenes. So this is the physical properties point of view. We've also demonstrated volatile organic compound detection with MXene, where we can detect methanol, ethanol, IPA, ammonia, also water. So this is critical for environmental sensing, because if you have this installed within the International Space Station or a submarine or any room that you will have several types of VOCs. The volatile organic compounds released by the breath of humans, by the just presence of the humans, would have to be captured in the environment to understand if it's going to be suffocating for someone, if there's too much of a VOC, or is that going to be also indicative of some kind of a existing condition. So imagine VOC monitoring can also help disease monitoring within a certain confined space. So these are some of the aspects that we've already tested. We're also developing several of these for breath analysis, because we want to understand internal organ behavior that would change and how that would actually affect your breath and then the VOC that could be captured. So this is also something that we are working on. So with all the background story of developing this for this terrestrial application, we are looking at combining nano and biomaterials with MXenes combined with bacterial cellulose, which my colleague Agatha has been producing in large scale for the last several years. And we've tried to make several types of sensors. We have also tried to demonstrate this in the stratosphere. So we had a stratosphere flight in sometime in 2022, and we've had about 8 to 9 missions after that, where we try to understand what is the change of the resistance of this material with the changes that happen with your flight that goes up to like 25 or 30 kilometers high. So that's the initial demonstration we wanted to do in stratosphere. So all this led to what we want to talk today about MXene in LEO. So MXene in LEO is a technology demonstration mission where we're using multifunctional nanomaterial MXenes with sustainable bacterial cellulose, which is basically the wearable device that the Polish astronaut tested in the space. But we also had two objectives for the mission. One is to understand how MXenes behave in the environment in ISS. So that was the fundamental question that we wanted to first answer. To see if you have MXenes in space station, how does it behave for the changing environment, for the changing pressure, for the changing temperature, humidity. So if there's a repressurization that happens for the Columbus module, can we measure that with our sensors? So for now, I think we can. We're also looking at some of the data that we have as reference sensors to match it with reference data with sensors which are already available commercially. So what you see here is basically the AstroPi, the computer on the onboard ISS. There are 4 of such computers on ISS. We built the data acquisition system with the MXA part, where changes in resistance can be captured through the 6 devices that we have. And this is the more interesting part for all of you, where the MXene wristband was actually made, integrating MXene with cellulose. And this was to demonstrate that we can capture pulse of the human subject, but also the hand dynamics of the human subject. Why is this important? Because if you're looking at long-term missions, extravehicular activities, you would want to know how precisely the hand movements have been used for a particular activity outside the space station. So you're imagining turning a screw. It might be easy with your hands, but with the suit on, it's not the same thing. So can we measure that? So these were some of the thoughts we had, but to ask some fundamental questions, does it work in space? So that's where we had 6 devices sent to space, connected to the data acquisition system. We also had the wristbands that were actually tested. So the MXA part is where we have tested this for the environmental sensing within the Columbus module next to the ANITA 2 module that was already present. So we had 2 venting systems close to it, so we can capture the changes in pressure that happens within the system. But follow through, like the next part is where you have the main part, where you have 6 devices of the wristband. Okay. Something happened. Okay. So we had 6 bands sent to the ISS, tested by the astronaut, while 6 bands were stationed on the ground for testing at the lab as an analog mission. But we also had pre-flight and post-flight testing of the devices we have. So this is something where we wanted to have repeatable results that we could actually utilize for the technology demonstration. Going through to give you an initial view of how the bands look like in the initial stages, it's basically where you integrate the nanomaterial into the biomaterial. So we did the demonstration on the ground. I think the video should work, hopefully. So the demonstration on the ground was done, I think, sometime in October, where we could capture the pulse. We could also capture finger movements, the hand movements of the ground subject. So this was the basis on which we designed the final model that was flown to the space station, and then the testing that was done. The last part, where you might find some more interesting results, is what happened to the bands when they were tested in the ISS. So we had a set of procedures that every human subject, be it on ground or in space, could test. We divided into 5 stages, where when you wear the band, so imagine if the band is my watch, you can have the wrist outstretched, the hand open, that's the still phase. Then you can close the wrist, bend it towards you, hold it for 15 seconds, then relax, still phase where you open the wrist, and then the 4th phase where you rotate your wrist 5 times, clockwise, anti-clockwise, and in the last phase, on-demand pulse measurement was done. So continuous measurement of pulse is something which requires energy all the time. So can we do it on demand? So we had, based on the medical procedure, having 2 or 3 fingers on your pulse on your left hand. with the sensor on, you can measure the pulse that comes from it. So what you see here is basically the response from the bending. What you see here is the response from the wrist rotation. So we have found this to be repetitive on ground, before, after flight. In flight, 14 sessions were done. In the last phase is where we get the pulse of the astronaut. So this is interesting because we didn't know that it would be so successful, because we thought we'll capture the pulse, but not the whole pressure wave that can come from it. So what you see here is basically the data which is cut down based on the medical data, medical board norms, where you see the pressure wave shape that we've got from the MXene wristbands, which is quite similar to the peripheral pressure wave that is an invasive measurement. So can we do non-invasive measurement of the pulse pressure waves? So this is something that we wanted to test, and the cardiologist in our team wanted us to take it forward. So not just from the lab to the space, but also to the hospital. So we're now doing a preclinical study with about 160 patients in the cohort, where we already have 40 patients enrolled and tested. So this is at Katowice, where we have the cardiology division, which is actually supporting us to get the tests done. Recently, yesterday, we also had the parabolic flight, where we have tested the MXene sensors with commercial sensors for lunar regolith movement. That is also something that we just demonstrated yesterday. And the final part is where we want to collaborate with the Military Institute of Aviation Medicine. We've been having discussions where we want to test it for 1 to 9G and also maybe micro G simulations with the MXene wristbands, which could be wireless, which could be more comfortable for the pilots to wear. So we've been working also on several applications where we have Ukashwich network partnering with us for the VOC sensors, which we want to use them as environmental monitoring devices in the ISS in future, or maybe the Star Lab. But then we also are looking at the usability of these bands for physiotherapy and rehabilitation. For assume a case you have some kind of an accident and you have wrist broken or the hand having some surgery, that is something that we want to see if we could use that. We're also now aiming much bigger than what we've done. We would want to make the MXene nanomaterial in space and also the biomaterial bacterial cellulose in space. So we're collaborating with ESA Biotech on developing the whole hardware, which can be demonstrated either in the ISS or a free-floating body, which could also be a in-orbit demonstration of manufacturing. And this is just the start. We also would like to see how we can take it forward for several of the applications with the military here as well, so that we can use them for applications for electromagnetic shielding. We can use them for applications for hypersonic hypervelocity re-entry vehicles. That is also something that we can have coatings made for. So that's it. So I would like to end by saying MXenes is just emerging as a main material for the future. And what you see here is just the first few steps where an advanced material has been taken to the space station, demonstrated, brought back to the Earth, and implemented in the hospital environment already. Thank you all. Thank you so much.
Thank you very much. And I'd like to open the floor for any questions before the coffee break, if you have any. Anyone wants to start? Okay.
So my question is to Shreyas. Yes, I want to ask because I've seen that you have in MXene you have layers. How many layers do you have, and can you change the layers? Because from this the properties could change. And the other is that did I understand well that you use tribology effect to switch, so to translate, to transduct the movements to electricity?
So we prepare few layers or single layer material of MXene, then assemble them together either through screen printing, spin coating, or through the processes of film formation. So then you self-assemble them into a laminar structure of, I think, maybe hundreds of such layers, because the individual layer is about 1 to 2 nanometers, and the lateral dimensions based on processing can be up to a few microns. Based on the processing method, we can have lower or higher number of layers together. But they are in a form of a multi-layer structure when they're formed. Then we process them to have single layers because they have better properties, and then reassemble. For the other question is basically we use the piezo-resistive method, where the change in resistance is what we are looking at. So we're not looking at change in electrical properties like voltage with the piezoelectric effect. So and also on the wristband, we're looking at the measurement of the pulse or the flow of the blood through the veins, which is basically converted into contraction and expansion of the skin, which is transferred to the sensor. Yeah, thank you.
Any more questions? All right, I guess we're conclude. I mean, you have a chance to chat to our panelists during the coffee break as well. And because next session is going to be the last one, and we already had a bit of delay due to the trip to the centrifuge, fun stuff that we did today. So let's go for a coffee break. I would invite you to get coffee and just bring it here, and we'll carry on with the presentation. So just a 5-minute break, get coffee, get yourself coffee, and get some sugar, and come back, please.